In this section, chapter 23, section 10, we're going to talk about amines as nucleophiles. And so we previously have seen amines act as nucleophiles if we use an alkylating agent like methyl bromide or something. We can alkylate an amine, and we can do polyalkylation, get a quaternary ammonium salt. But we're going to look at it as how do they act as nucleophiles on carbonyl groups. So we saw this before in chapter 18. If we take a primary or secondary amine and react it with an aldehyde or a ketone, well, the primary amine will react and give us an imine, and the secondary amine will react with an aldehyde or ketone to give us an enamine. We can also react ammonia, primary amines, and secondary amines with acid chlorides or acid anhydrides to give us amides. And so we saw that in chapter 20. We can also use amides as a protecting group. If you go back to chapter 16 and you look at when we talked about Friedel-Crafts alkylation and acylation, if we attempt to do a Friedel-Crafts alkylation on our strongest activating group, which is aniline, we're going to find that that lone pair of electrons on the nitrogen is such a strong Lewis base that it will react with the aluminum chloride, which is a pretty strong Lewis acid, to form this salt. And that is a very strong deactivating group. And so you can do no Friedel-Crafts reactions on this, because remember, Friedel-Crafts reactions don't work when you have strong deactivating groups. So I showed you a way back then how to get around this, and that is to convert your aniline into acetanilide. So if you take aniline and you protect it with acetyl chloride, you can make acetanilide. Acetanilide is still an activating group. It's not nearly as strong of an activating group as aniline is by itself, but it is still an activating group, still an ortho-para-director. And so since it's not as, it doesn't have as much electron density on that nitrogen, it doesn't act as much like a Lewis base and react with your aluminum chloride. So you're free to do Friedel-Crafts alkylation or acylation. And so here, if we do the Friedel-Crafts reaction on this, we can get our Friedel-Crafts products, the ortho and para product, because it is an ortho-para-director. And then we could do hydrolysis on acetanilide, which will give us aniline, the aniline product. And so there we go. That's how we do that. So we're going to look at number 24. Number 24 is a synthesis problem. So we'll switch over here to our in-class assignment. And so here we're trying to synthesize this particular molecule. Since we're trying to synthesize that particular molecule and we're starting from aniline, I have aniline right here as our starting material. The first step that we're going to take for either of these is that we're going to protect it using the acetyl chloride. So we'll use CH3COCl, right? And that will convert it into acetanilide. NH, and then we'll get that. So that is going to be our starting point for both of these. So we'll take this, convert it into the acetanilide, and then we're going to do our Friedel-Crafts reaction. For this top one, we're going to want to use tert butyl chloride as our Friedel-Crafts alkylating agent. And so we'll use the, I'll just go ahead and put that there. So Cl, so that's tert butyl chloride and aluminum chloride. That will do Friedel-Crafts alkylation and give us our product. All right, now I'm going to draw it sideways so I can fit it a little bit better here. So hydrogen, carbonyl, so that's our acetanilide. And then we'll have that tert butyl group that's in the para position. We're also going to get some in the ortho position, so I'm going to put plus ortho, and that just indicates that we're going to need to do a separation, probably some chromatography to separate the ortho and the para from each other, because we're going to get some of each, and I don't know what those percentages would be in this particular reaction, but I do know you wouldn't get 100% of one or the other. All right. Then at that point, we're just one step away. We just need to take this and do hydrolysis. So H3O plus and H2O. You potentially could use base here instead of H3O plus and water. We could use hydroxide and water and do hydrolysis. And really, which one you use depends on what your other functional groups are. With this one, it doesn't really matter. So we'll just use the acid. All right. As far as making this particular reagent, so we're going to use this as an acid chloride and do our Friedel-Crafts acylation in this case. So 1, 2, 3. That acid chloride plus aluminum chloride. And we would get, again, I'm going to turn this a little bit sideways so it fits in here a little bit better. All right, we'd get that. And then and again, I'll go ahead and make the note that we're also going to get the para isomer. So at that point, again, we would need to do some separation to separate out our ortho from our para so that we get the one that we want. And then we can convert that into this compound by using hydrolysis. So H2O and acid. Again, you could potentially use base here, just like with the other one. All right, so let's go back and look at the next thing. All right, we're now going to talk about one of my, I don't know, it's one of my favorite. I say that about a lot of reactions. I really like this reaction because it gives you an additional tool when doing elimination reactions. So amines typically don't do eliminations very well. If you attempt to do an elimination with H and NH2, you're not going to have a good day. It's not going to eliminate very easily because we have a really poor leaving group. NH2 minus is a pretty dismal leaving group. But we can do a trick where we convert that poor leaving group into a good leaving group and then heat it up and we can do our elimination. When we do this, we call this Hofmann Elimination. It's a very clever tool, and there's an advantage that I haven't talked about yet. I will talk about that in a few minutes. So let's look at the details for doing Hofmann elimination. So very first thing, there's 3 steps. Very first thing is that we're going to take our amine and convert it into a quaternary ammonium salt. We'll do that by using a very good alkylating agent, in this case methyl iodide. That's an excellent alkylating agent because iodide is such a good leaving group. So we'll alkylate this, and when we alkylate this, we'll get this quaternary ammonium salt, and that quaternary ammonium salt is a less bad leaving group. I wouldn't say it's a great leaving group, but it's not a bad leaving group. So the trick now is that we're going to take this and we're going to react with that iodide. Usually once we've lost this as a leaving group, we don't even think about this, but we're going to lose that iodide. We're going to react with that iodide with silver oxide. Silver and iodide react pretty well with each other to give silver iodide. It's a pretty stable compound. It precipitates in water, if you recall. All right. And so then that's going to give us the silver iodide as a precipitate, and we'll have this hydroxide left over so that we have a hydroxide salt with this quaternary ammonium ion. And then it's just a matter of heating that up. We have this hydroxide, which acts as the base so that we can do the E2 elimination across this alpha-beta bond to give us this alkene. And our products here are H2O. That's part of why we heat it up, is to help drive that water off. And then we will get this tertiary amine as a leaving group. So again, we don't consider that a great leaving group, but it's a much better leaving group than NH2 minus. Miles better. So, all right. Well, let's look at the mechanism. We're going to look at that last step of the mechanism a little bit more closely. It does follow the E2 mechanism. So that means that we're going to simultaneously make a new bond between oxygen and hydrogen to form H2O. We're going to break the bond between this carbon and hydrogen. We're going to make the new pi bond between the alpha and beta carbons here. And we're going to break the bond between carbon and nitrogen to give us this amine. So all of those happen in a single step. That's a simultaneous reaction. That's why it's considered an E2 reaction. Elimination has to occur anti-periplanar. We'll find that the syn-periplanar doesn't work very well, and so it does need to occur by an anti-periplanar geometry. In other words, the hydrogen and our leaving group need to be oriented on opposite sides of the molecule. That has an important implication when it comes to stereochemistry, and we'll talk about that here in a few minutes. Let's look at an example of doing a Hofmann elimination. So here we've got two examples actually. So here we've got cyclohexanamine, and we can do our alkylation of that amine to give us our quaternary ammonium salt. Reaction with so that gives us our quaternary ammonium salt, which makes it a good leaving group, or at least a better leaving group. We're going to react the silver oxide with the iodide, and then that will create hydroxide as a strong base that is part of the salt, all there, ready to do elimination. And then we add heat to do the final step of the elimination. The heat, without the heat, it doesn't happen because we need that heat to take advantage of our increase in entropy caused by this reaction. So that gives us our product. Here, if we look at this other one, this is the 2-phenylethanamine, and we can do elimination on it to form styrene. I will tell you this is not the most efficient way to form styrene, but I'll explain why it is we do this kind of reaction to begin with. And it's not to form styrene, and it's not to form cyclohexene. It's to form things that you wouldn't form when doing a regular E2 elimination step. So now we're going to get to the regioselectivity of Hofmann elimination. And this is the cool part of Hofmann elimination. It's the major difference between regular elimination and the E2 mechanism that we saw way back in the first semester. When there are constitutional isomers that are possible when we're doing elimination, the major alkene product is not going to be the Zaitsev product, so it's not going to be the more substituted product. It's going to be the less substituted product. So if you recall, when we do elimination, if we had this, it was an OH, and we used acid, protonate it, and we would do elimination, we would find that we would get a more substituted product. We would get elimination between here and here. But with Hofmann elimination, we get the less substituted product. So we get this as our major product, and the more substituted is our minor product. So this is sort of anti-Zaitsev. Now, I don't know if anybody uses that term, but it's the opposite of Zaitsev elimination. All right. The reason for this is that we have this very large leaving group, and that means that the base must approach from our less substituted beta carbon. And that's because that less substituted carbon is going to be more accessible. It's going to be easier for the hydroxide to come in from this side and eliminate here than it will be to come in from this side and eliminate here. And that's our rationale behind why we get the less substituted elimination product. So let's look at a couple more examples of this difference in regioselectivity. So we'll start with this 2-bromopentane. If we do elimination with 2-bromopentane and use one of our regular sterically hindered strong bases like potassium tert-butoxide, our minor product is going to be less substituted, and our major product is going to be the more substituted alkene. We can form both, but we'll get more of the more substituted alkene. And of course, we will get both the E and the Z isomer, so we'll get that pair of diastereomers. Probably more of the E because it's a little bit more stable, but we're going to get both of those. So that's what happens in a typical E2 reaction. But in the Hofmann elimination, our Hofmann elimination product is not going to be Zaitsev. It's going to be where we get the less substituted product. So again, we convert this into a good leaving group. We create the hydroxide, we heat it up, and we're going to get our less substituted alkene as our product, and our minor product will be a little bit of the more substituted product. So let's look at numbers 27 and 57. And on these two problems, the first part of this problem is just looking at regioselectivity. The second part, number 57, we're going to look at stereochemistry. So let's switch over here. So we want to draw the major product that is formed in each of these. So on this one here, we've got potassium tert-butoxide. This is our typical E2 conditions. And there's two possible products here. We can get elimination here or elimination there. If we get elimination between carbons 2 and 3, that's going to be our major, it's going to be our more substituted, and in this case, the major product. So our major product here would be 1, 2, 3, 5, 6, and we'll get a double bond there. So that's going to be our major product. We could potentially get some of elimination between carbons 3 and 4 here. That is a possibility. All right. All right, I'm going to scoot this a little bit this way just to help with the light a little bit and the angle there. All right, so we could get a little bit of that elimination product, but we're going to get mostly this. With this one, it's going to be the opposite. Instead of eliminating between carbons 2 and 3, our major product is going to be to eliminate between carbons 3 and 4. So we get that as our major product, and I will go ahead and put plus the Z isomer. For this particular compound, that's the E isomer. The Z isomer would be where these two alkyl groups are cis to each other. We would get a mixture of those when we do the Hofmann elimination. All right, here again we're comparing regular E2 elimination with a sterically hindered strong base versus Hofmann elimination, which will give us a different regiochemistry. So on this one, we should get elimination between carbons 1 and 2. And so that should be our major product when we're doing that elimination. When we do elimination with this one, we should get elimination here between those. I didn't mean to draw that there, but we should get elimination there. And that would be our major product for that one. All right, for the next part of this, we're going to look at number 57. And on this one, the regiochemistry is already determined for us. We're going to eliminate down the carbon-carbon bond that represents the front carbon in this Newman projection and the back carbon in this Newman projection. And the hydrogen and the NH2 have to be opposite each other for this particular elimination. So we're going to eliminate across this carbon-carbon bond. This nitrogen is on the back carbon, the NH2. That, of course, is going to get converted into a quaternary ammonium salt when we do Hofmann elimination. And then we're going to eliminate this particular hydrogen. What makes it so that we can't eliminate the other ones is that Here on this carbon and the adjacent carbon there are no hydrogens adjacent, so we can't eliminate there. And then here we have a phenyl group, which means there's no hydrogens there to eliminate. So we really only have one option for doing this elimination. Now, on this one, it's set up already so that it's in the correct orientation, so that this NH2 and that hydrogen are already anti-periplanar to each other. And since they are anti-periplanar to each other, we just need to take into consideration which groups are going to be cis to each other. So these two will be cis to each other, and these two will be cis to each other. Now I'm going to take the front carbon and put it on the left. So I'll put front carbon over here on the left, and the back carbon I'm going to put on the right. And so for that front carbon, we've got a methyl that is attached to it. Okay. And on that front carbon, we also have an ethyl that is attached to it. All right. On the back carbon, we've got this phenyl group, which is on the same side as the methyl. So we'll have a phenyl group, which is C6H5. And I'm just going to write it as C6H5 rather than write it out the whole phenyl group. And then our tert-butyl group is on that same carbon. So we'll have that tert-butyl group that is there. All right, and so that's the particular diastereomer that we get with this particular elimination. Now for this next one, we want to get this NH2 and this hydrogen anti-periplanar to each other. And so it's best if we redraw this Newman projection to get them anti-periplanar to each other. It doesn't particularly matter whether we rotate this front one or the back one. I'm going to rotate the back one. So I'm going to draw our circle here, and then I'm going to leave the front in exactly the same configuration. So NH2, C6H5, and then here we've got our tert-butyl group is there. And then for our back carbon, we're going to rotate this hydrogen so that it's anti-periplanar to this NH2. This ethyl is going to rotate up to be CH2CH3, and then this methyl is going to rotate over here to give us that. All right, and then once you get here, it's pretty easy to see, and I'm going to do the same thing. I'm going to circle these. These two will be cis to each other, and these two will be cis to each other. So now when we do the elimination here, I'm going to take the front carbon and make it on the left. So this is the front carbon, and the back carbon I'm going to put on the right. So let's do the front carbon first. This front carbon has a C6H5. So C6H5, and the front carbon also has a tert-butyl group. So CH3, 3. And then on the back carbon, we're also going to have two things. The back carbon will have a methyl. The methyl will be cis to the phenyl group, so CH3. And the ethyl will be cis to the tert-butyl group, so CH2CH3. If you analyze these two, these are identical molecules. All right. You'll see that the phenyl and the methyl are cis to each other, and the ethyl and the tert-butyl are cis to each other. And we have the same thing. So phenyl and tert-butyl are on the same carbon, and methyl and ethyl are on the same carbon. So these are the same molecules. It's just we're looking at this from the opposite side as this one. So it's like we took this one and turned it over, and now we're looking at that. All right. Now for this one, we're going to rotate around here. And again, it doesn't particularly matter which carbon we rotate. I'm going to rotate the back carbon just like I did in the previous one. So we'll draw the circle here, and we're going to put everything in the front in exactly the same place. So NH2, we've got tert-butyl here, so CH3, 3, and then here C6H5, our phenyl group. The hydrogen, I'm going to rotate from here to here. All right, and then the methyl will rotate down here, and then this ethyl will rotate there. So again, we're rotating about that carbon-carbon sigma bond to get this set up. Once we have that, we can then analyze which groups are on the same side as each other. So here we're going to have phenyl and ethyl that are on the same side, and tert-butyl and methyl are on the same side. I'm going to use the same thing where I put carbon. I'm going to use the left carbon as this front carbon, and the back carbon I'm going to make the right carbon. And it's just a matter of putting in what the substituents are. So here for this, I'll put the phenyl here, so C6H5, and on that same carbon, we've got the tert-butyl group, so CH3. So here you'll see this is in the same orientation as these two. For the back carbon, we've got ethyl and methyl. The ethyl is going to be on the same side as the phenyl group, so we'll have CH2, CH3, and our methyl will be here. And if you look at this compared to these are diastereomers of each other. One is E and one is Z. So one is E and one is Z. And if you're wondering which one's which, let's see. These are E and this one is Z. But these are diastereomers. I ran out of room there. So diastereomers, you can figure out what I'm saying there. So those are diastereomers of each other. Let's come back over here, and I am going to, I went through and I figured out what the stereochemistry was on each of these. So I figured out the RS configuration for each of the two carbons, the front and the back carbon here. This one on the top is the RR isomer. And feel free to take that molecule, you can build it, and then confirm for yourself that that one is the RR isomer, and this one here is the SS isomer. So since these are exactly opposite, these are enantiomers of each other. So these those are enantiomers of each other. When we look at this one, the front carbon on this one is S, and the back carbon on this one is R. And I'm just going to indicate it that way. So we have RRSS, those are enantiomers. On this one, we have one that's the same and one that is different from each of these. And so that means that this is a diastereomer with both of those. So this is a diastereomer of this, and it's also a diastereomer of this. So these two are these two are enantiomers, and this is a diastereomer of both of those. If we took the enantiomer of this, so instead of the RS, we have the SR, we would also get the same product. As an extra problem, try to convince yourself that that's true. All right. All right, so we're going to briefly talk about reactions of amines with nitrous acid. So what happens when we react amines with nitrous acid? What kinds of compounds do we get? So nitrous acid is a weak acid, HNO2. And if you, it's not stable, it's not particularly stable. You can form nitrous acid by taking the salt of that nitrous acid, so like sodium nitrite, and reacting it with HCl. So you can protonate this and you'll get nitrous acid. Well, if you have more of that strong acid, then you can protonate the nitrous acid as well. When you protonate that nitrous acid, it will form an even more unstable ionic compound here, it will lose H2O. And when it loses H2O, we're going to form nitrosonium ion. The nitrosonium ion is a very electrophilic species, and it is very good at reacting with amines. And so once we form this in solution in the presence of an amine, this will act again as an electrophile to react with the nucleophilic amine. So let's look at what happens when that occurs. Well, we're going to get something that we call diazotization. So diazotization. In diazotization, what happens is that we convert the amine group into a diazonium salt. So the NH2 will get converted into N2+. And so because that is going to have a positive charge, if you look at that in nitrogen, it has a formal +1 charge on it. And we need a counter ion, so whatever our acid was, the counter ion of that is going to be the counter ion of this, so it will be a diazonium salt. Now, we can either form alkyl diazonium salts, as in this case, or we can form aryl diazonium salts. However, the alkyl diazonium salts tend not to be very stable. Even at room temperature, even below room temperature, these will decompose to give off nitrogen and all kinds of other reactive intermediates. So we tend not to make these as often. Now, there may be certain situations where we want to make this, particularly if we make it in situ and then use that as a really good leaving group, but otherwise we tend not to make them. The aryl salts, on the other hand, are very useful synthetically, and we're going to talk about those in more detail. All right. Now, one thing I want to note before I go to the next page is that both of these were primary amines. This was a primary alkyl amine, and this was a primary aniline. So there were no extra substituents on the nitrogen. When you have primary, you're going to get the diazonium salt. All right. Let's look at the mechanism for a primary amine reacting with the nitrosonium ion to give us our diazonium salt. So the very first step is that we're going to react our amine with the nitrosonium ion. All right, so we got this earlier. I showed you how we make nitrosonium from sodium nitrite and HCl. It's a couple of steps. We have to protonate the nitrite ion to form nitrous acid, and then we protonate that nitrous acid. It decomposes and gives us the nitrosonium ion. So we get nucleophilic attack of the amine on that nitrosonium ion. That gives us this intermediate, which we need to deprotonate to give us this N-nitrosamine, so N-nitrosamine. And if we started off with a primary, then we should still have a hydrogen here. If we start off with a secondary amine, then we're going to have an alkyl group there, and that's where it's going to stop. But for the primary amine, we have a couple more steps. So on this, we're going to protonate that nitrosamine. All right, we protonate that nitrosamine. All right, that gives us this. And then we're going to use the counter ion here to deprotonate that nitrosamine, the intermediate, that is. That will give us this. And then we're going to protonate that again. And then H2O is going to act as a leaving group, and that will give us the diazonium salt. And so that is how we form the diazonium salt. So there's a lot of protonate, deprotonate, protonate, deprotonate that is going on in this. So let's go back here and look. So nucleophilic attack, deprotonate, protonate, deprotonate, protonate. So we have a deprotonate, protonate, deprotonate, protonate, 4 in a row there. And then loss of H2O to give us that diazonium salt. All right, so let's look at what those alkyl diazonium salts again, just to mention why it is that they are unstable and why it is that we tend to avoid them. So they are not as useful synthetically. When we form the alkyl diazonium salt, well, that N2 plus is a really good leaving group. The leaving group would just be N2. N2 is a very stable compound. It's a gas. It bubbles out of your solution. And so you're left with a carbocation, and that carbocation could do any number of things. The chloride can come in and react with it. We could do elimination reactions. We could do rearrangements, hokey pokey, right? You stick your alkyl in, maybe not the hokey pokey, but we get a lot of different reactions going on with them, and that's why we tend to avoid them. Now, again, there may be certain use case scenarios where we want to do this kind of thing, but usually when we're doing diazonium salts, we do it with aryl diazoniums. All right, we're going to very briefly talk about what happens when we take nitrosonium. We react nitrosonium ions with secondary amines. We get something where it stops. We don't go all the way to the diazonium because we can't do that extra deprotonation where we remove that hydrogen. So the nitrosonium ion will react with secondary amines and aryl amines, so both alkyl and aryl amines, to form N-nitrosamines. So here we've got a secondary amine. We do our diazotization conditions, but instead of getting the diazo, we get this N-nitrosamine. So this N-nitrosamine. Well, this was just an intermediate in our previous mechanism. However, here, because there's not a hydrogen to deprotonate, this is our end point in this reaction. One of the downsides of these N-nitrosamines is that they are pretty potent carcinogens. And we'll find that they are found in some foods and also found in tobacco products, including some of the e-cigarette products. And so this particular N-nitrosamine that is found in there, this is something you don't want to be breathing into your lungs. But if you smoke, it is something that you will breathe into your lungs. Now, it is by no means the only carcinogenic compound present in cigarette smoke. There are literally hundreds, thousands of these potential carcinogens. Again, public service announcement, please don't smoke. And if you do smoke, try to quit. All right. And so they don't go any further. We stop there. And again, the whole reason they don't go any further is that we don't have a hydrogen here to deprotonate in that step in the mechanism. The mechanism for the formation of these is just like the first page that I showed you on the formation of the diazonium salt. It just stops at the N-nitrosamine. So we're going to look at number 28 on our in-class assignment and see what we form under these conditions. So draw the product that is formed when each compound is treated with our sodium nitrite and HCl. If we have a primary amine, we're going to form a diazonium salt. If we have a secondary amine, we're going to form an N-nitrosamine. So in this case, this is a primary amine. It's an aryl amine. So when we do our reaction, we're going to form a diazonium salt. So methyl N2 plus and then chloride. And it will be a salt. So that will be a salt. And then there's all kinds of reactions, and we're going to talk about that coming up here in a little bit. We can take this and do all kinds of cool reactions with that. All right, here we have a secondary amine, and since that's a secondary amine, that means we're going to form an N-nitrosamine. So we'll draw that part of our secondary amine, and then we'll draw a nitrogen, and then a double bond going to oxygen. And I'm going to go ahead and put the lone pair of electrons on that nitrogen just to emphasize that that nitrogen is sp2 hybridized. So that nitrogen is sp2 hybridized. There's still a lone pair here, so this nitrogen is technically sp3, although I think there's some resonance structures we could draw for this. I'd have to look. Yeah, so we would have that there. Okay, let's look at this one. Again, this is a secondary amine, which means we're going to form an N-nitrosamine. All right, so we'll draw the amine part of that, and then we'll put the nitroso group on there. So the N, oxygen, and we have a lone pair of electrons on that nitrogen. All right, finally here we've got an alkyl amine, and so when we take this, let's see, we're going to form a diazonium salt. So 1, 2, 3, 4, N2 plus, and then chloride. Because this is an alkyl diazonium salt, it's probably unstable. So I'm going to go ahead and put that this is likely unstable. So likely unstable. All right. So although this is a fairly short video, at least compared to some of the videos that I've put up, we're going to stop here and we're going to put the rest of the video onto the rest of this chapter onto a separate video. So stay tuned for that next video. There's some cool reactions that we're going to do with those diazonium salts. So some very cool reactions.